This is a talk about building microservices that are based on Kafka as sort of the backplane, and then using Akka Streams and maybe Kafka Streams. I want to talk a little bit about the pros and cons of each choice, what I like about them, what I think you should be aware of, and I'll even show some code examples. As usual, I put photographs that I've taken in the decks that have absolutely nothing to do with the subject, except there's a lot of water pictures, so streams, I guess. These happen to be from Glacier National Park up in Montana. So let's start by putting streaming in context a little bit. This is actually the same lake as the previous picture, but earlier in the day. I wrote a little Reilly report that you can get for free on our website about, almost 2 years ago now, that kind of goes into the way I see things shaping up as far as doing streaming data processing as opposed to like normal big data batch processing, what those architectures have to account for, what they have to support. And so a lot of what we're talking about is kind of a summary of what's in this report if you're interested in more details. And I'll have that link up at the end, and also the slides will be available. So if we look at the architecture that I think is kind of emerging as a best practice architecture, if you will, it looks something like this. This is a little busy, and we're not going to go through all of it. The numbers come from the report itself, but we're going to focus on a couple of areas in this talk, or in this diagram, and that is Kafka as the data backplane, where it's kind of connecting everything together, and then these two APIs, Akka Streams and Kafka Streams, that you can embed in your microservices to do data processing. So first, let's talk about why Kafka. Well, Kafka is a log-oriented system. It's not really a message queue because the consumers do not consume the messages, which is what a normal queue would do when you pop an event. Instead, consumers can start at whatever offset they want in this ordered log and start reading. They can go back and reread if they've made a mistake, if they've crashed, or whatever. And Kafka keeps track of the life cycle of each of the elements. Normally, it's like a timeout. After a week, they get deleted, something like that. And you can have as many producers as you want, writing to the log, as many consumers reading it, and so forth. And it's designed for large scalability, for partitioning these topics is the way things are organized so that you can scale horizontally and so forth. So a given topic might be a logical thing that you're interested in, like let's say credit card transactions if you're a bank. And then for scale, you might partition them maybe by something like zip code or the customer state that they live in or whatever. The order is guaranteed in the partitions, but not per topic. So you don't get global ordering over the topic, but you do get ordering in each partition. It also has some important architectural benefits. So I drew this diagram deliberately bad, meaning hard to understand. It's a complete bipartite graph where I've got data sources on the left and sinks on the right. And the problem here is not only is this hard to comprehend if I'm sort of the architect trying to sort things out, but suppose service 1 on the right crashes, then I've suddenly got these broken links with all of these sources, and I could have data loss. And somehow I've got to, even if I restart service 1 quickly, I have to communicate to everybody on the left. Here's the new address to be writing data to, and so forth. There's a lot of problems with these kind of direct connections. Well, as we all learned from computer science, you can solve any problem with another level of indirection. So we'll just stick Kafka in here, and that solves the problem. And it does actually solve the problems that I just described in a couple of ways. One is it's conceptually simpler what's going on. I sort of have this universal pipeline or enterprise service bus, if I can call it that everything is flowing through. So conceptually, it's simpler. It's also simpler, like for the APIs. If I really take this to its extreme and do everything through Kafka, then the only API I ever have to know is the producer and consumer API, for writing to and from Kafka. I don't have to understand, any ad hoc API for some REST service or whatever. That's probably going too far, but nonetheless, it has that benefit. And then the last one is this resiliency argument that, if service 1 crashes now, then I'll have data accumulating in Kafka, reliably and durably. The services on the left don't have to know anything about this problem. They can keep, writing as always. And then when service 1's replacement comes up, it picks up where it left off. I can also scale these things independently. If service 1 is getting overwhelmed, maybe I can spin up another instance of it to balance the load, that sort of thing. Okay, so to summarize, it simplifies our dependencies. It gives us some resilience against data loss. So we can have an arbitrary number of producers and consumers, and we do get kind of a simple, uniform way of gluing everything together. But it's sort of the analog of the database that you're writing stuff to. In fact, some people even talk about Kafka as kind of a database in sort of a streaming way instead of kind of the usual relational way. But there's obviously stuff you need to do with the data once it's there, and that's what the streaming engines are for. What am I going to do with these records that I've captured? Now, in that report I mentioned, we actually talk about 4 of them. Well, really 5 if you include Beam, and I'll ignore that one for right now. But I want to contrast with 2 others that you might use first before coming back to Kafka and Akka, and that is Spark and Flink. These are basically services that you run in your environment. At least the normal way you deploy them in systems like Hadoop is you have these daemons running around the cluster and you submit work to them and they figure out how to break up that work into tasks. They do all the parallelism for you. They manage those tasks. If anything fails, they restart them and so forth. Flink works in a very similar way. They just do a lot of heavy lifting for you, and they do a great job of handling very large data sets where you really do need the parallelism of a cluster in order to partition them. And so they're really good systems, and there's just a whole lot going on when you submit a job to Spark, and Flink is very similar. The program that you write is called a driver typically. That's like the main process it's going to run and kind of orchestrate everything. And then it talks to some cluster manager process that knows how to split things up into these individual tasks that are running under the supervision of an executor on each node and on and on and on. And the other thing you get with this is this automatic partitioning. You also get this pipelining effect. So if I do read this data set and then map and filter and flat map, well, all of that can be pipelined together without running separate tasks for each of those steps. But then if I do a group by or join, well, that might require data to be shuffled over a cluster, and it handles all that, and then starts the next pipeline and so forth. So just a whole lot going on under the hood. And it might immediately raise the question, well, why wouldn't I use this if it turns out I'm not going to get a lot of that kind of automatic stuff with these other toolkits? And the reason is that they do impose a fair amount of overhead. They do have higher latency than tools like Akka Streams and Kafka Streams. And maybe they just don't fit the model that you're working in. Maybe you want to glue lots of other kinds of code into that streaming pipeline that you're writing. And it's a little harder to do that with with Spark and Flink. So there are times when I think you really do want microservices doing your data processing and not these kind of, let's call them big ticket systems like this. But it'll all depend on what you're kind of trying to do. Actually, there's another reason it's worth mentioning why I think that the balance might tip towards microservices over the long term. And that is that normally when you're doing stream processing, you're actually working with a little bit of data at a time. That's not always the case. You might be joining in legacy data, historical data, and so forth. But the chances that you actually need the parallelism that you're getting on this diagram diminishes, I think, if you average over all the jobs you're writing, when you're doing things a little bit at a time versus capturing like data for a week and then suddenly processing it all at once. So that also makes it easier to do a microservice approach. And the final thing I'll mention is that if you really know how to run microservices well, you've got everything tuned for monitoring and management and deployment and your CI/CD pipeline and all that stuff, it's nice to keep using that model for everything, even if it happens that Spark would be fine, let's say, but it doesn't quite fit into that infrastructure. Okay. So instead, we'll talk about these streaming alternatives. And these are really libraries that you embed in your microservices, whether you've written them with Akka or Go or Node, or, well, actually Node would be a little tricky. Actually Go would too, because these are JVM processes. But the point being that they are designed as libraries that you embed in the system. They are not systems that you throw work at, like the other tools. Okay, microservice, all the things. Well, we use microservices when we decide that, we have too little latency in our system and we want to add latency, or, when we don't like the reliability of function calls, we'd like things to be less reliable. And if you accept that argument, then let's talk about microservices. Now, this diagram I came up with to kind of set the stage for understanding sort of the worldview of Akka Streams versus the worldview of Kafka Streams. And there's really kind of a spectrum of microservices in this context. The kinds that we're used to writing, I think, are more on the left side. They're more about event processing, like login user, authorize credit card, add item to cart, things that sort of imply state transitions. I'm going to do something unique with each of these events. They affect a particular customer, and I may route them in different ways, and so forth. Whereas on the right-hand side, I'm arguing that on the other side of this spectrum are things that actually are a little more anonymous. They're more like records of data that I'm shoving through the system, and I can process them a little bit more en masse, or at least conceptually. So, each item has an identity when we're talking about an events. The difference between an event and a message is a message has a sender and receiver, but it could be encapsulating an event. I often process them uniquely, at least logically I think about this. I might do some sort of bulk processing for efficiency. And often they're used to drive sessions, state machines, and that sort of thing. Whereas in the other case, if this works, there it goes. Here I'm thinking I'm just going to shove a lot of stuff through. I'm going to do something like a SQL query. Group by this, filter, select these fields when this clause holds, or where clause, that sort of thing. So I think that's important because to me, Akka Streams emerged out of the left-hand side. It started as this great microservice toolkit, and then Akka Streams is this, streaming DSL on top of it. But it really has that mindset of I'm processing events, and I need very fine-grained control over what I'm doing with this data. If you went to Colin's talk before this one, he went into a lot of detail about some of the cool things you can do with Akka Streams. And a lot of it is really powerful little operators you can apply to your data, like send the error messages this way and, group things up for efficiency and then send them in bulk and, handle timeouts and all this kind of stuff. The sort of thing that you really need when you really have tight control over your environment and need very fine-grained control over what's going on. Whereas Kafka Streams really emerged out of the data-centric world, in my opinion. Now, if you went to Nia's keynote yesterday, Nia's one of the early engineers on Kafka. They do talk a lot about event sourcing, event processing, microservices in the same way, and you can certainly use Kafka Streams for all that. But if you look at the kind of things that they give you as easy-to-use tools, to me, they really fit the model of we're processing data. They give you like a SQL query engine now and things like that. So I think that they fit better on the right-hand side. So let's dive into these two toolkits. First, we'll talk about Kafka Streams a little bit. So some of the things that they give you that become important when you're doing like aggregations, like I want to average what's happening over, I don't know, how much money am I making per hour? How many items have I sold per SKU, per store in my online store, that sort of thing. So they have some important concepts like the difference between event time and processing time. Event time is what you really care about. That's logical time. That's when something really happened against somebody's clock that matters. Whereas processing time happens to be that machine over here that's doing the analysis, and it could be, in sync with event time on the other machines, but realistically, it's always off a little bit. And it might be processing this data, days or maybe seconds or milliseconds after it actually happened. And that's what the diagram's designed to show on the right. If I was doing some sort of analysis every minute, statistics of any kind, I can't just say, all right, I just hit the minute boundary. I'm just going to calculate whatever I've got from the last minute, because I've got stuff arriving late, stuff arriving at different times just because of normal time of flight in a network, and also for worst case time of flight when I have like partitions, where maybe I won't see the actual data for some machine, hours later. What do I do about all that? So they've started thinking about how to handle these kinds of things, going towards the model of giving you accurate analysis of data based on these sort of time windows. The last bullet point, this is actually a big subject, and it's a very important subject when you get into more advanced streaming scenarios. And I talk a little bit about it in that report and then reference some even better writing about it by some guys at Google, for example, Tyler Ackadow being one of them, who's really gone into this in a lot of detail. Kafka Streams, made a big splashy announcement about this time last year that they had implemented exactly once processing. Those of you who are pedants would know that that's impossible. You can never actually do exactly once, but you can if you set your boundaries at a certain level. If you basically do at least once and then automatic deduplication, then if you are exactly once, as long as a meteor doesn't strike your data center, that sort of thing. So we like to say it's effectively once, if we want to be really careful about it, but it's logically exactly once. And just as a reminder, although I think with this crowd you get it, at most once is fire and forget. It may never get there, but nobody cares. You might do that with some telemetry, some log messages. At least once would be, I'm going to keep trying until I get an acknowledgement, but you may end up with multiple copies. And then exactly once is this sort of unicorn of you only see it once and you never miss anything. Now here's another example of where they've thought about the data problem. They have this abstraction called a K-stream, which is really the normal stream that we've kind of been talking about with Kafka, where I just want to see the sequence of events. It's like an event store kind of picture. But maybe I don't really want to see the whole thing. Maybe I really want to see something that's more like a database. I just want to see the last value for a key, or I want to run up an aggregation that I'm going to keep updating in place the way we would do with a traditional database. And they use the K-table abstraction for this. So these are really nice features they built in to make it easy to do these kind of typical things that we do when we're analyzing data without having to write a lot of boilerplate ourselves. But there are some limitations, though. Kafka Streams only talks to Kafka Topics or in memory. So if you want to have it reading a REST interface or writing to REST or writing to a database or something, you have to put in something else to do it, some other library or whatever. Or just you could embed the logic in the stream code itself, but that's normally not what you really want to do. It's really not designed to connect to the rest of the world in the same way that Akka is designed to do this with Alpaca. And the way you do scaling and load balancing is really by partition. It's very centric towards concepts in Kafka like topics and partitions, and that's how you scale. There is a Java API. Lightbend actually contributed a Scala API that's now in the project, and I'll show you an example of that in a little bit. And as I said a minute ago, there's even a SQL API, so you can write SQL queries, which is unbelievable, but actually SQL has become like the favorite DSL in streaming like everything else, it turns out. It's kind of a crazy thing that's happening. So anyway, let's look at an example. This is sort of a sketch of what it is, and because we're talking Kafka Streams, every little bit of logic will read and write Kafka Topics. In this case, I'm going to assume I'm ingesting a raw stream of data, and I'm going to send it into two separate places. First, I want to send it to some machine learning model training. Maybe I'm looking for anomalies, or I'm going to do recommendations or something like that. So that'll be one pipeline. And then out of that model training, I'll get periodic updates to the model so that it stays current. And I'm going to ingest those new model parameters and the raw data into this model serving bit at the top. And that would be, somehow I'll have this process that updates my model when new parameters come in. And then whatever happens to be the current model, I'll score data as it comes through, like make recommendations, flag it as spam, whatever it is I'm doing. And then I can send that downstream, the scored records, and do other stuff, which I won't really go into, but just to show you what it might look like. So I am going to use this new Scala API that Lightbend wrote. Here's just a bunch of details. Several of my colleagues worked on this. And there's also kind of a neat API that we didn't contribute. It doesn't really fit into the Kafka project, but if you use the query ability to ask stuff of state, you can actually query a stream for its state while it's running. Then this link at the bottom is a tool to make that a little easier to do. Okay. And the example itself is taken from a tutorial that we have on GitHub if you're interested in playing around with this stuff in more detail. Obviously, I have to greatly simplify the code for a short talk. Okay, it's a lot of code here, and I'm just going to walk through it carefully. Well, not too carefully. I'm actually going to skip over some details that aren't that terribly important, but just to sort of hand wave about some of those at first here. I'm going to assume that I'm going to read some Kafka topic called a raw data topic, and there's the usual thing you do to configure where that is. You talk to a Kafka broker, and it tells you where to look for it and all that kind of stuff. We won't go into those details. I'm going to need a couple of other topics like the model topic, which is where I'll write model parameters when I've trained a new model and so forth. I'm going to need something that handles those updates to the model, and it's not terribly complicated logic. It depends on what toolkit I'm using, but we'll just abstract over that idea as well here. The next thing I'll have is this model, which will be the thing that manages, oh, you just sent me a new bunch of parameters, and now I need to figure out what kind of model you want me to implement. I'll spin up an implementation of that model and then put it into the stream. And then we'll have a notion of some data record that encapsulates whatever it is we're actually scoring, whether it's credit card transactions or people surfing on my website, whatever. And then scored records would just add whatever the score is. And then finally at the bottom in the red box is just some sort of configuration object that is required in Kafka Streams. It tells you things like, here's where you can find the brokers for Kafka. Those are the kind of the master processes. Here's the topics I want to use and so forth. All right, so I'm skipping over all those details to get to the gist of what life is like writing a Kafka Streams app. You would start with this stream builder. That's like your entry point. Now the S at the end is actually the Scala wrapper addition to this. For the most part, the API that we wrote, we tried very hard to make it just a thin veneer over the Java API so that conceptually, if you know the Java API, you can easily write with the Scala API. There's no new concepts added and so forth. So it's just a very simple change at the top to start off with the Scala API. Then you ask the builder to create two kinds of streams for you. In this case, we're going to be reading and writing bytes of arrays. And just to, it's kind of to take the worst case. Kafka Topics, generally speaking, are just big blobs of bytes. There are ways you could layer schema on top of them, but we're just going to go with the worst case and manage it ourselves. So we're going to need two of these streams, one of which will be the raw data. That, again, from that, well, I guess I put the diagram in the bottom. That'll be the first gray box. And then also I'll need a stream for my model topics. Here's something, again, that's going to process updates to the model. We're skipping over the details there. And similarly, I'm going to have some object that encapsulates taking that model, taking a record, and then applying a score, giving me a recommendation, marking it as spam, et cetera. And then this is code that probably looks a lot like what you're used to if you've written any kind of collections API code in Scala. If you've written Spark code, it's very similar, et cetera. Where I'm going to start with the model that the model stream that I built. I'm going to map over the input values. And what I'm going to do in this first step is parse those bytes into a new model. And this is actually going to return, let's see, what does it return actually? Oh, it returns a record of this stuff. Then I'm going to filter over the ones where I successfully parsed into the model. So I've put in a little logic to handle that. Then I'm going to map over those values to take the model parameter set and turn it into an actual implementation. And then the last step is where I'm going to actually process this to set up the model in memory so that when I do what's sort of like a join later on, I'll have my new model in memory. The data processing stream is very similar. It's a little simpler in some ways. Again, I've got raw bytes coming in. I'm going to have something that knows how to parse those bytes. I'm going to look for success or failure on that process. And then if I succeeded, then I'm going to take each record and I'm going to create a new scored record by calling my scoring object that we saw towards the top and just give me a result for this thing. And then the last line is where I'm going to actually send it to the output. 2 is going to write to yet another topic in Kafka where I send these results to. And then the last thing you do, you actually build up a topology. So you call this Kafka Streams object to take the builder to construct a topology of stuff in memory that will actually do this. You pass it this config object. You start it running. And then you can add a shutdown hook if you want to clean everything up when you're done. So this code, I think, is conceptually pretty simple. You know, there's a little bit of fluff here in the way that the tutorial handles bytes and parses things into models and so forth, but not too difficult. Hopefully, it's reasonably comprehensible if you've ever written any Scala collections code before. But there are some things missing, actually, and that is that the library is doing a really nice job talking to Kafka, giving us these processing primitives, maybe exactly once if we care about that, as we said. But boy, there's a whole lot left to do, right, to actually run microservices. So you're going to embed this in whatever your favorite library is, which probably is the reactive platform from Lightbend, I'm guessing. But even if you like another JVM-based library, you would just embed this stream code into that to run your microservices. And we'll come back to some production concerns in a little bit. But let's now talk about Akka Streams. I'm sort of preaching to the crowd here a little bit, or choir rather. It does implement the reactive streams standards so that we get backpressure for free for flow control. Okay. And if you haven't heard of that, basically the idea is that you have this back channel of communication. So data is flowing left to right through some sort of queue. The problem with the queue is that if it fills up and it's a bounded queue, then I have to throw data away on the left-hand side. If it's an unbounded queue, I eventually run out of memory if my consumers can't keep up. So how do we solve this problem? Well, we have this communication protocol of sending information from the consumer back upstream to the producer to say, I can take as much as you can send me right now. That's great. Just push it as fast as you want. Or, I'm actually kind of slow up here. Why don't you just send them one at a time? I'll actually pull. So it actually toggles between those kind of operations, push and pull. But it means that you can not have to worry about having something blow up in the middle, which is really the key thing. It's really a simple idea, actually, but it had never been done before, at least in our context. And it's really powerful as a way of building things that actually compose, because backpressure propagates through the whole system. So you can have an entire network of these things that won't kill each other by overwhelming themselves. And then you can make strategic decisions. So instead of some guy in the middle having to make the decision about what do I do when I can't push any more data in this queue, instead somebody at the beginning can decide in a strategic way, all right, this is what we're going to do if we run it. If we can't keep up, maybe we'll spin up a whole new copy of the topology. Maybe we'll just throw data away. Maybe we'll write data to a file and feed it in later. We can make those decisions strategically. So we get all this with Akka Streams because it implements this. It is part of this big Akka ecosystem, so all the things I just mentioned about how am I actually going to run this in production when I've got all these other concerns, there's a whole lot of stuff that we can do. Even if you're using the Kafka Stream API on top of Akka and so forth, you can use all of these tools for HTTP, for persistence, and so forth. And in particular, I mentioned Kafka Streams can only read and write Kafka Topics. Well, with a library like Alpaca, you can connect almost anything you want. So here's the gist of an Akka Streams app. I think, and I don't think anybody at Lightbend would disagree with me. We haven't done a great job giving you really easy, here's the gist kind of documentation. So I sort of created a little example that I thought would at least give you kind of the bare bones minimum thing that you would have to write. So let's walk through this a little bit. So you always start with a source of some kind. Here I'm just going to do a source of 10 integers from 1 to 10. And I'm going to define some flow that will operate on the source. Now I could have more than one source here and more than one sink if I want, but again, to keep it simple. And what I'm going to do is scan my source. What scan is actually letting me do is accumulation. I'm going to start with a count of 1, and then I'm just going to multiply by each number and build up a total. So it's basically like fold left or something like that for those of you pedants out there. Anyway, so that's what I'm going to do. I'm going to count the numbers from 1 to 10, or actually multiply them in this case. And then I'm going to run with it. It encapsulates something we'll see a little bit later where it materializes this thing into actual actors. And then I'm going to tell it, I want you to just send it to println. So we're actually going to not dump it to anything new like a topic in this case. We're just going to print out the results. So the gist is source, flow, and sink is sort of the minimum thing for an Akka stream. And this is actually defining a graph. So you can have fairly complicated graphs. Colin showed some interesting ones that, from practical examples in his talk earlier. Now the diagram here is showing one slight difference, and I put the other one in the bottom just for comparison. And that is that, when I have something like an actor system under the hood, maybe it doesn't actually make sense to run everything through a Kafka topic because there's some overhead there. Maybe in some cases I should just send stuff as a message to another actor to do some follow-on logic. And once again, I'm not going to show anything as an example for that logic, but this is an option I have with Akka Streams, is that I can balance that choice, and I'll come back to that choice in a little bit. But first, let me go through some code for how this works. Those of you who've used Akka will recognize a lot of this. Once again, there are some things that I'm not going to go into any detail about, but are pretty standard things. The first block, the actor system, the actor materializer, these are the sort of things you always do. They're your entry point to create this stuff. So you start with those. The model processor and score, that's basically the same thing that we just talked about, just sort of abstraction around managing models and actually scoring data with those models. We're going to use kind of the same concepts of a record and a scored record. Now you can see I'm going to define a data source. And then there's this thing on the two types, or one is the record type. So that's like the schema of the data in this source. The second item is like a control construct. It gives me some hooks for doing additional things with this stream if I want to. I kind of glossed over that part in the earlier example. Let's see. You can see the middle block, there's subscriptions topics. So consumer, subscription, I think producers down there. These are sort of the Akka Streams libraries for talking to Kafka. And I think that's it for that block. All right, so let's actually go through the example. So once again, we start by creating an actor system, like we would if we were just writing regular actors. But we also need something that can materialize the actual runtime graph that's going to process this stuff. And we're declaring these things implicit because they're just carried along as arguments to some of these methods, but we don't want to have to specify them explicitly. This logic here is basically the same as what we had before for Kafka Streams. But now what we're going to do slightly differently is we're going to leverage the ability to actually define our own custom stage. This is like our own controller or operator. So I can treat this model scoring stage that I'm going to create as if it was a regular operation that I can apply like map and collect and so forth. And without going into a lot of detail, it looks basically like this. I extend some abstract class. I give it this particular name. I define what they call inlets and outlets. These are the data coming in and going out. And then I define a handler that's going to process each record as it comes in. And in this case, what it's going to do is, this is what I'm going to use to score data. So that scoring record object, or record score object, whatever I called it, is going to be called to construct a new scored record with each record I pass in. I think there's a typo here, actually, but oops. Anyway, I think you get the gist of it. It's just a nice mechanism for defining our own custom operators, which is the sort of thing you would do if you wanted to give this toolkit to machine learning researchers who didn't want to have to worry about those kind of details. All right, I kind of reversed the order a little bit. Previously, I talked about the model stream first, then the data stream. Here we're doing it the other way around, but very similar. With some interesting exceptions. Now, the Akka guys they're very careful about terminology. They don't want to tell you something that doesn't exist, like exactly once. So they'll say consumer at most once source in this case, or it could have been at least once, et cetera. And then it's up to us to handle deduplication or whatever. Although with at most once, we really only see things once or 0 times. So we're going to go with that sort of reality dose here by going with that most once. The data consumer settings is like my configuration for how it knows to talk to Kafka. So we're going to then subscribe to the data topic again. That's the blue arrow or sort of cloudy like looking thing in the diagram. And then we're going to map over this, parse it into a record. And then we're going to use collect, which is sort of like filter, but also supports transformation. So in this case, the data record parse bytes will return either a success or failure. And so what we'll do is collect, we're going to say, all right, if we got a successful parse, we'll just pull the data out, and that will be the thing we send downstream. Otherwise, like any good production code, we're just going to throw away our errors and ignore them. Okay. So otherwise, we should really have a case for the failure situation as well. Now, the model stream, this is really very similar to what I said before. Following the example from the tutorial, we're going to try to parse the bytes. All right, now we've got information about the model if we succeeded. Then we're going to try to figure out which model we want to build. The reason this logic is there is the tutorial supports things like I actually want to use a TensorFlow model, or I want to use logistic regression. And so that's sort of metadata that would be buried in the model parameters. And if that all succeeds, then I'm going to build up my new model processor, set the model towards the end there. And I'm not going to do anything else with this. I'm going to actually, as my sink, just have it ignore. It's not going to write anything out. I'm just going to take this object. The reason I'm not writing anything out here is I've actually circumvented the stream, if you will, with model processor set model. Everything I care about is actually going to get passed to this in-memory object. So there's now nothing left for me to pass downstream. So I'm just going to write to basically a no-op sync at the end. And then the data stream is kind of similar to what we had before, where I'm just going to hopefully succeed in parsing. If I don't, then I'll just ignore the result, and I'm going to run with a producer that will actually write to a new Kafka topic. So the run with will, and then a producer will give me a sink that sends the records downstream. Okay, a lot of code, maybe a little hard to follow when I'm going through it quickly, but hopefully you get the gist. To kind of wrap up, I want to talk about a few production trade-offs that you might think about. One is, how do I score this thing? Well, there's several things you can do in the architecture itself. There's different techniques that have emerged in the model serving community, if I can call them that, of like delegating work to worker nodes. We've got all the facilities we need in Akka to do this kind of thing very easily. There's also a cool idea of I might have several different kinds of models, and I pick the winner. When I score a result, I have a metric that says whether this result is more likely to be right than this result, and tricks like that. I can connect to almost anything with Alpaca. So I could, instead of going through Kafka, I could just go directly through a web interface, like data coming right off the internet or something if I really wanted to, and so forth. I can persist state if I want to keep track of the model in case things crash and bring it up really fast. I could use Akka persistence for that. All right, now let's talk a little bit about something I alluded to a minute ago. When would I not want to go through Kafka? And when would I want to go through Kafka? The advantage of like a direct actor-to-actor call is it's extremely low latency. It's little more than a function call. Very minimal I/O and memory overhead. And I don't have to do any marshaling of the data to send it across a process necessarily. That's a bit of an exaggeration, but it gets rid of a lot of the things that happen when I go out of process. But it is harder to scale, and there's a slightly more direct dependency or connection between the guy that's sending the message and the guy receiving it versus the kind of abstraction we get going through a Kafka topic. Now that can be abstracted through actor references and so forth, but it's a little bit more of a coupling. Whereas if I'm going through a Kafka topic, I am taking on higher latency, the whole network traffic and queue depth. If I'm going through the messages one at a time and I have a very long topic partition, then I get overhead or latency from that. I have to marshal data. I have all the I/O of going across the process, but I get a lot of flexibility for stability. I'm much more of a firewall situation where if a process crashes, it's unlikely to affect Kafka. I can easily scale up and scale down more easily in some respects, and so it has its advantages too. I get backpressure with reactive streams if I'm just doing streaming messages between things. That's not true if I'm doing actor message calls, but if I'm using streams to communicate, then I get backpressure. But once again, I do get a little bit more of a direct connection between sender and receiver if I'm using actor messages. Whereas on the right-hand side, I get a really deep buffer. It's not quite infinite, but it does kind of mostly solve that problem of why reactive streams were invented, which is I can't have infinite buffers. Well, I can have a nearly infinite buffer if I have a big hard drive, is basically what it comes down to. But it's not infinite. And I get strong decoupling. So you have to kind of balance when it makes sense to run things through Kafka versus when it actually makes sense to get better efficiencies by keeping it in process. So to wrap up, again, this is kind of summarizing what was in this report. Obviously, we're building commercial stuff around this, and you can come talk to me afterwards if you're interested in our fast data platform. And actually, IBM is showing it too in their booth. And that's it. Thank you very much. I think we've got 5 minutes if anybody has questions or criticisms, complaints.
Hi, I have actually 2 questions. We're using Kafka Streams, and at the beginning we added FS2, but eventually we saw that we don't need it. We thought about using Akka Streams, but we again found that we don't need it. My question is, which use cases do you think where Kafka Streams is just not enough? That's my first question. My second question is regarding your interactive queries library, which you embedded Akka HTTP strongly with it. Would you think if an interactive query which is distributed is a good idea? Because it's like counterintuitive, because usually you would like to go to the local storage, to the RocksDB inside your service and not starting hopping between services. So yeah.
Yeah, let me pop the stack on the questions. As far as so that query library I mentioned in passing, what happens is you can ask a Kafka stream for its state rather than have to force you to write something that writes to a database and then you query the database. The problem is out of the box, it only lets you talk to a single process. So if I have a family of Kafka Streams apps, because I've got a bunch of partitions, 1 app per partition, then I have to ping each one of them. So what this library does is it makes it easy to aggregate that into one big query. That's really all it does. Does that make sense? I think it makes sense for things like dashboards or something that maybe aren't quite mission critical. I'd be a little hesitant to just rely on this mechanism if I really needed that state to be persisted in a robust way. I would rather somehow either write it out to Kafka or write it to a database out of band in some way. But I think it's really a nice tool for these kinds of less mission critical kind of queries of state. But I think people are actually using it for that purpose, but it's probably more risky because it's not really designed in the same kind of robust way. As far as the limitations of Kafka Streams, I think Colin's talk was a really good example earlier of if you really need fine-grained control and want very precise handling of how things flow through the system, but want to express it in practically a declarative way rather than writing a lot of Akka code, it's a fantastic tool to go to Akka Streams for that. It really fits that model of I do have very tight constraints of how things should be processed, and I want to do very robust error handling and error recovery and routing of messages and all that. Whereas I think Kafka Streams really comes into its own for more, let's call them mainstream scenarios, like I'm just going to do ETL. I've got log messages coming in. They're just strings. I'm going to parse them into a record format for downstream analysis. Or, I've got a dashboard over here, and I've got a bunch of topics that I just want to watch, like aggregated information, like high water marks or average over time. It's really quick and easy to knock out those kind of applications in Kafka Streams, but they don't give you the kind of low-level, powerful control that you get with Akka Streams. So that's sort of the intuitive way that I think about the differences. Is there anybody else? No. I don't see anybody either. All right, thank you very much.